In section 3.6, we're going to begin discussing how you can graph using calculus and calculators together. Because we know that you're going to be using calculators or some software at some point, like MATLAB, for example, or Desmos. How can you use the two things together in a way to be able to still pick out important information, but also as a way of sort of speeding up the process? So how can we do that? Even with graphing calculators and math plotting software, important information is missed. One of the standouts to me is inflection points. This is something that I don't know if I've seen a software that can accurately pick out inflection points, for example. In this section, we will discuss how to use calculus together with graphing software to accurately sketch the graph of given functions. So that's just one example, would be inflection points, but we'll see in another example that yet another piece can be missing. Okay, so we have in example 1, we have this function. It doesn't look like it's too terribly bad, but it is absolutely awful. You'll see this when you start taking derivatives of this thing. It is not easy to work with. So this is why we're going to use the calculator to help us pick things out. Okay, so consider this function. So use the graphs of f and f prime to estimate the intervals of increase, decrease, extreme values, intervals of concavity, and inflection points. These are things that the calculator kind of struggles with, where we can use the calculus to help this out, and then sort of key into the strengths of the calculator, which is just simply graphing. You can do an excellent job with that. So the first thing that I wanted to point out is that we're going to have some vertical asymptotes. So wherever the denominator would potentially be 0, wherever the denominator would be potentially 0, that's going to be an asymptote as long as it's not at x equals 0. But we can see that x equals 0 does not make the denominator 0. So the question is, where is this equal to 0? So the simplest way of doing this is just to simply, let me just open up Desmos as an option here. Desmos. And we'll type in that function. Y equals x cubed plus x squared plus 1. This is just a very simple task. We're looking for zeros. And what's nice about Desmos is you can just use the wheel button on your mouse, just kind of zoom in real quickly, zoom in and out real quickly. And in fact, it picks out important information here. Here's the important information. Right here, we have the 0. So we have a 0. Let's go ahead and write that down. So the 0 of approximately negative 1.4656. That's going to be the approximate 0 there. Which is, this is the equation of the vertical asymptote. Okay, so that's what this represents here. Now, let's go ahead and calculate the first and second derivative like we were asked to do. Okay, so the first derivative isn't too terribly bad. We're just going to rewrite this function as x times this denominator to the minus 1 power. Or actually, excuse me, how am I going to do this? Yeah, I'm just going to use the quotient rule as is. I'll just use the quotient rule. So we're going to square the denominator. You can do what I said, but I just want to follow my work that I have in the paper because, like I said, the derivatives get pretty awful pretty quickly here. So you square the denominator, bring the denominator up, and leave it alone. Differentiate the numerator, gives you 1, and now you do the reverse. Differentiate the denominator, gives you 3x squared plus 2x, and then you leave the numerator alone. Okay, so this is what we have, and we can rewrite this as, let's see, so if you just combine like terms, there's nothing to really factor out of the numerator. So you just distribute, combine like terms. So basically what you would get is this. You would get minus 2x cubed minus x squared plus 1. That's what you get for the numerator. And the denominator, we're just going to bring this up because I do not want to use the quotient rule again here. I think I tried that my first time through, and it's just awful. So it's awful because we're going to have to type this into the calculator, and it just makes it even worse to type it into the calculator. Okay, so the second derivative. Now we can just use the product rule taking the second derivative, and here's what we'll get. It's very simple. We're just going to, the process, we're going to differentiate this first term here, gives us minus 6x squared minus 2x. And then we're going to leave this term here alone. Okay, and then we're going to do the reverse. Plus, we're going to do the reverse. Okay, so when we do the reverse, we're going to differentiate this. We have to do this using the chain rule. So it's going to be minus 2, what's in parentheses there, to the minus 3 power, times the derivative of what's inside. Here, this is minus 3. Let me emphasize that. Okay, times the derivative of what's inside, which gives us 3x squared plus 2x. Okay, and then we're going to leave this term here alone. Times minus 2x cubed minus x squared plus 1. Okay, so as awful as this looks, this is better than going through the quotient rule in terms of what you have to type into your calculator. Now we're going to get out our graphing calculator. We're going to type the first derivative in there, and we're going to type the second derivative in there. And just to save a little bit of time, because it takes some time to accurately get this in there, you have to type it in exactly what it looks like, basically, with the parentheses and all. So type that in. Here's what you would get. Now, if you go up and down, you can make sure if the parentheses are sort of blacked in or filled in like this, then it's going to show the graph of this. These other two that I have typed in are not going to be shown because it's just going to be a mess trying to graph three things at the same time. This is the first derivative in y1, and y2 is the second derivative. I'm going to go to zoom decimal, and we have the graph. So what we're going to do here is we're going to pick out the critical points. The critical points, this is the derivative. The critical points are where it crosses the x-axis here. So these two locations. Now here's how we can find these exactly. So let me go to calc. Second trace here takes us to calc, and there's a 0 or root finder. So you just go over to this left one. You need to give it a left bound. I went a little bit too far. There we go. So just go a little bit to the left of the 0. Hit enter. Then go a little bit to the right of the 0. Hit enter. And then you want to pick a guess, and you can go either way because you don't really get any closer. I'll just hit enter again. And then it produces this. So negative 1.465571. Not a very nice number to work with, but that's what we got. And then you'd want to find this 0 right here as well. Now, to the left of this critical point, the derivative is negative. Between the two, it's positive. And to the right of this second one, it's positive. This is the sign of the derivative. So we're going to fill out a sign chart here. Let's fill out a sign chart for the for the first derivative. So here's our sign chart. We don't need to do any test points because we're using the calculator to basically test. Okay, so here's what we get. So negative 1.4656. Oh, I missed one. 0 is also a critical point. Let's go back. Something is not right with this graph. Why is 0 a critical point? No, that's not correct. I just had 0 marked on there for some reason. Okay, yeah, it's just these two critical points. I thought maybe I had a mistake. And then the second one here is, if you use the 0 finder, it's 0.6573. I'm going to keep I'm going to make sure that these are both accurate to 4 decimal places. Just stay consistent with everything here. Okay, so from our sign chart, we know that it's positive here. We know that it's positive in between. Excuse me, hold on. Excuse me, it's negative to the left of that. Let's fix that. I'm trying to remember what we had from the graph. Let me fix that. So it's negative over here, positive in between, and then it switches to negative over here. So that basically tells us where F is decreasing and increasing. So it's decreasing here, increasing here, and decreasing here. Now keep in mind that this particular critical point here that we're talking about, negative 1.4656, this is a vertical asymptote. So that's what we have there. If you see from our first slide here. So that's the equation, the vertical asymptote right there. All right. Let's look at the second derivative. And again, I quickly type this in here. We go back to y equals. Let me just unhighlight the equation here by the equal sign and highlight this equal sign so that we get the second graph. This is the second derivative. We're already in zoom decimal, and that's a good fit for the graph. I think this is going to work here as well. And this is what we get, the second derivative here. All right, we have a couple things going on. Notice that negative 1.46 right here. This is a vertical asymptote. And this vertical asymptote, the vertical asymptote of the original function is also a vertical asymptote of the second derivative. Sorry, I just caught something. I noticed that if we had a vertical asymptote in the original function and we had it in the second derivative, why do we not also have it in the first derivative? So I paused the video here for a minute to see what was going on, and long and behold, there was a typo. It's difficult to type this big mess in accurately, all of this stuff that we have here. I forgot a -2 exponent on that second term. Now let's go back and look at the first derivative again and fix things. Now we've got that vertical asymptote at negative 1.46 roughly. Okay, and then we have to find, we have a 0 right here at 0.6573. And if you trace over, let me hit trace. So you'd use your zero finder to find that, like we talked about just a second ago. But if you scroll over just to see what happens, is there any other zeros that you would have? If you're looking at the signs of the y's, it's still negative, still negative, still negative. It looks like it remains negative if you just keep on going. And in fact, if you think about it, if you take a limit as x tends to infinity, you're going to have you'll see you have a horizontal asymptote right on the x-axis, and that's kind of what's going on. So let me go and fix the zoom here. So zoom decimal. All right, so this asymptote here, that's a critical point. That's where the derivative is undefined, negative 1.46, and then this other one here that we'll find, that's the 0.65. Let me go back and fix our sign chart. Here is the correction to our sign chart now. So here, this is actually positive right here and here. Positive in between, and then negative. So this was actually increasing here. Okay, so let's move on to the second derivative now. Now we have our sign chart for the first derivative. Let's do the second derivative. So again, go back to y. We're going to unhighlight the equal sign, but then do it in the second derivative here. For the first derivative, we unhighlighted y1, highlight y2, go back to the graph, and here we go. We're going to do the exact same thing. We just want to put a sign chart together. So basically, we're going to have to find this 0 right here. Just use second trace, which is calc, to find the 0 here, find the 0 here, find this 0 right here, and then you're just going to trace over and see what happens if you go out to see if it crosses again. You're going to look at the signs. You're going to do the same thing to the left, but I've already done this. This is going to be positive over here. The sign of the second derivative, it stays positive. It stays positive over here to the right. And then in between, it's negative, positive, negative, positive for that tiny little bit. And then we can fill out our sign chart. So let's fill in what we have. So basically, this is the second derivative now we're looking at. It's going to give us information about the function f here as well. And so here we wanted to know above what the sign is. What is the sign of the second derivative? Okay, so we have that same critical point, and vertical asymptote location is also going to be a possible inflection point. And then here's some other possible inflection points. We had one at negative 0.4900 there. 0, and then way over here is 1.1002 to keep them all accurate to 4 decimal places. So what we have over in this portion is that it's positive, it's negative in this portion, positive in this portion, negative, and then finally positive. So that tells us information about f. It says that it's concave up in this portion, concave down in this portion, concave up again, concave down, and then concave up. So there's our sign chart for the second derivative, and we had our sign chart for the first derivative. So we had all that information that we were asked to find off of the function. There's one other thing that we should do. I don't think we were asked to do this, but this is something that's optional. It says use the graphs of f and f prime and f double prime, to estimate the intervals of increase, decrease, extreme values, intervals of concavity, and inflection points. We're gonna pick out the key points because what we have here, we have a whole bunch of inflection points. We have this is not a critical. We have a critical point right here, which turns out to be a, what is this? This is increasing to the left, decreasing to the right. It's going to be a maximum at this location on F. So this is a key point, and all of the sign changes here. This is an inflection point, this, and this. 4 inflection points, 1 max. We want to know what the corresponding y values are. Let me show you a quick way of doing that. So here's what we can do. Go back to our calculator. Now I'm just looking on the graph of the second derivative. You can do the same thing for the first derivative to find those key points. What you would want to do is in y4 or y3, for example, just in one of the other locations, just type in the original function. So you type in x divided by, this one's actually pretty easy to type in, x divided by, I'm trying to see from my paper, x divided by x cubed plus x squared plus 1. Okay, and then we want to unhighlight anything else, the equal sign. So we don't want y2 to show we don't want the graph of y2 shown. Okay, so it's just y4. Now hit graph. We don't care what we see. This is the graph of the function. We want to type in, or we want to hit second calc and value. We want to know what the y value is. So go back to your sign chart. Let me pick out the max that we had. There was a max at 0.6573. Here's the corresponding y value. And then you just write that down. You do the same thing for all of the other inflection points. Now let's go back and construct our graph. From these sign charts, we can construct an accurate graph. And here's what it would look like. I'm going to put in those key points first. So let's see, I'm going to have to go 1, 2, 3 to the right. I'll go 3 to the left as well. I'm going to go 1 up and 1 down. And that should be enough. so we can fit in all of that important information. I'm going to put in the asymptote, which is roughly at -1.5. It was -1.46 something. Just call it -1.5 roughly. And then we're going to put in all those key points. So -0.5, -0.5, that's one of them. That's one inflection point. Another inflection point is at 0, 0. Yet another is at about 0.65. Oh, what do these tick marks represent? Excuse me, let me fix something. I just caught something. These tick marks actually represent, on the x-axis, I want these tick marks to be at 1/2. Just to give us, so this is 1 right here, this is -1, just to be clear. However, this is 1 and this is -1. So I'm picking a different scale on the x and y axis here. Okay, so let's fix this. So -0.5 roughly, and -0.463. That's one inflection point right here. Another's at 0, 0. Another's at 0.65 or 66, 0.38 right there. Another inflection point way over here, just a little past 1, and it's at a height of 0.3 roughly. Okay, so if you read your sign charts, you're just looking at where things are increasing and decreasing, concave up and concave down. We have all of the important aspects of the curve, the key points, as well as the asymptote. We just fill all of this in, and here's what we get. It kind of swoops up to the left because it increases and it's concave up. And then it picks up from the asymptote. It's going to be concave down now up to this inflection point, but it's increasing. So this is what it look like here. Changes to concave up between the two. Still increasing, but changes to concave down up to this maximum. Then it stays concave down but decreases. It's a little bit hard to draw. And then it switches to concave up but increases. Or excuse me, it switches to concave up but decreases. And keeping in mind, looking at the original function, as x tends to infinity, the denominator has a higher degree than the numerator, which means that the whole thing is going to head to 0. So y equals 0 is the equation of a horizontal asymptote. So we know that it's going to do something like this. And since we found all of these key points, we know exactly what everything is here. So this maximum, for example, is 0.6573. We read that off the sign chart. The y value we get out by what I was just talking about is 0.3830. We have the location of these inflection points. Like this one here, for example, is 1.1002, comma, 0.3106. And then this one is just 0, 0, nothing fancy there. And then this other inflection point here is -0.4900, comma, -0.4365. So we have all of the important aspects. Nothing was missed here. And here's an accurate graph. And so you can see it matches up with our graph. Do I still have that? Yeah, it matches up with the graph that we had before. But we made sure that we didn't miss anything important. Let's go ahead and stop here with this video. If you'd like to practice some WebAssign homework problems, I think you can do problem 1, problem 2. Yeah, I think you can do the first 2 problems on the homework assignment.